I'm Sarah and I work in the computational magnetism group at the University of York. My PhD specialises in the atomistic modelling of anti-ferromagnetic materials. So in this tutorial we're going to go through how to model anti-ferromagnetic materials using the Vampire software package. So, anti-ferromagnets. I'm sure that we all know what an anti-ferromagnet is. They have a bulk magnetisation of 0, and this is because they're comprised of 2 or more sublattices, each of which are anti-ferromagnetically coupled to each other. So this means that the exchange constant, as you can see the spin Hamiltonian on this slide here, is negative. So the minimum energy configuration occurs when the spins line up 180 degrees apart. Because of this means that micromagnetic modelling is too simple to model the complex physics involved, because in micromagnetic modelling obviously you take, say, a 1 nanometer cubed part of the system, sum over all the atoms in it, and from that make a magnetic moment. But if you did that with an anti-ferromagnet, you would get a magnetisation of 0. So atomistic modelling is necessary. So how do we model our anti-ferromagnet? So we're going to start by modelling a really simple uniaxial antiferromagnet. So our antiferromagnet has a cubic substructure. It has 2 sublattices. So you need 2 materials in your unit cell file. The 2 sublattices have planes of anti-parallel magnetisation. So as you can see here, we've got 2 sublattices, one blue pointing this way and one red pointing this way. So we have 2 exchange interactions going on. We've got the exchange interaction from the red sublattice to the blue sublattice, or the blue sublattice to the red sublattice. And this is an anti-ferromagnetic exchange, so they tend to align anti-parallel. And then we have the exchange interaction between atoms in the same sublattice. So say here we've got Jij2, which is from red to red, but is also the same from blue to blue. And this is a ferromagnetic exchange, and it basically just acts to stabilise the system. So now what we want to do is we want to try and model this. As we know, Vampire can already model simple cubic structures. However, because we have 2 sublattices, this means that we need to define each sublattice as a different material, so that we can have different exchange constants between red to red and red to blue. This means that we can't just use the simple cubic structure already in Vampire. What we have to do is we have to create our own UCF file. So we've already gone through this in the skirmion section, so the unit cell file stays exactly the same. The only difference is our structure. So we need to create a different unit cell input file. So to do this, we need to define our unit cell. So what is the minimum repeatable magnetic and crystallographic structure? So for a normal simple cubic system, the minimum repeatable structure is 2 atoms. However, because we now have multiple materials, the minimum repeatable structure is now what we can see here. It's 8 atoms with 4 atoms from each sublattice. So what we want to do is we want to be able to repeat it. So if we took our unit cell and if we copied it, so if we have it here and we copy it in this direction or in this direction to create a whole structure. So this means that what we have to do is we have to define the positions of all of the atoms. So we've done that here. So if we just think of the first 2 atoms, so we've got an atom at 0, 0, 0, and then we've got an atom at 0, 0, 0.5. So if we imagine we've got our unit cell, and then if we copied it upwards, so we repeat it upwards again, so by the distance, so then we would have an atom at 0, 0, 0, an atom at 0, 0, 0.5, and then another red atom, which is a copy of the 0, 0, 0 atom at 0, 0, 1. So this is why we've put our blue atom at 0, 0, 0.5 and not at 0, 0, 1, as you would expect, because otherwise when you copy it upwards, the red and the blue atoms would be in exactly the same spot. And this happens in Y and in X as well. So what we need to do first is we need to list all of the atoms that we can see here in this structure and what sublattice they're in. And then we can use exactly the same unit cell format that we used for the skirmions. So we have 8 atoms and the atom IDs start at 0, so that should actually be 0 to 7. And then for each one, we need to put the X, Y, Z coordinate and then the material, so that's the sublattice. So in there we either put a 0 or a 1, depending on whether the atom was red or blue. And then we put a height and a width. We'll keep both of those for 0 for now. That's just an output parameter, but for now, for our simple system, just put 0 and 0 in both of those columns. So, as if you notice, for the unit cell size, we've put 2 times A. That's because if we look at this picture here, it's what we were saying before. So it goes from 0 to 0.5 to 1. So our total distance of our unit cell, where we want to copy the second red atom to, is a distance 2 times A away from the first atom. So that's why that's 2 times A, 2 times A, and 2 times A. Okay, so here is our unit cell input file. So our first atom, atom 0, is at 0, 0, 0, and that is in sublattice 0. The second atom is the second one, the blue one, is at 0, 0, 0.5, and that is in sublattice 1. We then continue this down for the rest of the atoms in our picture. So we need to define our interaction list. The problem with defining our interaction list is that interactions don't only occur within the unit cell. Each atom will also interact with atoms outside of its own unit cell. So this means that we need to create 26 unit cells surrounding the initial unit cell. So if we imagine one unit cell in the middle, and then we create a unit cell above, a unit cell below, one to each side, and then an entire cube around the whole structure, as shown in this picture here. So if we imagine our unit cell to be a cube in the centre, we've created all of these unit cells around this first unit cell. And this is just so that we can model any interactions with our unit cell, with atoms in the surrounding unit cells. So obviously the unit cell will interact with atoms in the unit cell, but also with other ones. So each atom should have 6 nearest neighbour interactions and 12 next nearest neighbour interactions. So for a normal simple cubic ferromagnetic system, you would only need the nearest neighbour interactions. But for our anti-ferromagnetic system, you need the nearest neighbour interactions and the next nearest neighbour interactions. This is because, if you remember from this diagram here, you have the nearest neighbour interactions, which are the JIJ1 interactions, which are from atoms in one sublattice to the nearest neighbour atoms in other sublattices, and you have the JIJ2 interactions, which are from atoms in the red sublattice to other atoms in the red sublattice, and atoms in the blue sublattice to other atoms in the blue sublattice. So this interaction is ferromagnetic and acts to stabilise the system. So this means that for every atom, what we need to do is we need to find the 6 nearest neighbours and the 12 next nearest neighbours. So this can be done by creating a short Python or C++ or whatever programming language you want to choose. And basically, so if we start with the red atom in the top corner, you can see that what you want to do is you want to calculate which atoms are nearest neighbours to it and which atoms are next nearest neighbours to it. So this is obviously a 2D representation of the 3D problem, but we should be able to get an idea of what's happening from the 2D representation. So if we take our red atom, and if what you do is you look at which atoms are closest to it, so you can see there's a blue one in cell 001, and there is a blue atom in cell -100, and then the 2 blue atoms that are in the same unit cell. So basically what we've done is we've given each unit cell that's been created around the initial unit cell a little code. And it's basically just the movement from the initial unit cell. So we've moved, so if we look sideways, we've moved, you've got -1, 0 and 1. And then we've obviously got Z, so if we look downwards, all the ones on the bottom are at 0, 0, -1, and all the ones on the top are at something, something, 1. And this basically just defines so that we can pinpoint which atom in another unit cell the atom is interacting with. So the program is quite simple. What it's going to do is it's going to loop over all atoms in the initial unit cell, and then loop over all other atoms in all the other unit cells, calculate the distance between the atoms, and see if they are nearest neighbours or next nearest neighbours or neither. And if they are nearest neighbours or next nearest neighbours, add them to the list. So we want to store the atom ID of both the atoms. So we want the atom ID of the atom in the initial unit cell, and then the atom ID of the atom that it's interacting with from either the same unit cell or another unit cell. So if you look at this red atom that's in the top corner of the unit cell, and if we say that this was atom ID 0, every atom in all the other unit cells that correspond to this atom has exactly the same unit cell ID, so they're all atom 0. The only thing that changes is the unit cell coordinates, so the dx, dy, and dz. So you could say, so I'm saying that the atom 0 from unit cell 000 interacts with atom 1 from unit cell -100. Okay, so this is what our unit cell file looks like for the interaction list. So we have an interaction ID, so we know that each of our 8 unit cell atoms is going to have 18 interactions, 6 nearest neighbour and 12 next nearest neighbour. And the next column is the atom IDs, so that's atom ID I and atom ID J. So I is always in our initial unit cell, and J is any atom it interacts with from any other of the 27 unit cells that we've created. So these always go from 0 to 7. Next we have dx, dy, and dz, which are the same coordinates that you can see in this picture here. So they're just the unit cell of atom J. So if an atom is interacting with an atom in the same unit cell, you say 0, 0, 0. And if it was interacting in with an atom in any of the other unit cells, you would use the coordinates for that unit cell, say 1, 0, 0, or whatever you want. So the next column is interaction strength. So we're using a normalized interaction. So this means that all of the interaction strengths have to go between 0 and 1. So you set the interaction strengths in the material file, so that's the .mat file, and then you just set the strength of the interaction compared to the value that's in the .mat file in the interaction strength column. So we can just set all of these to 1, and then we can just set the values in the .mat file. But sometimes you might want, say, some of the interactions to be weaker than others. But for now, we're just doing a simple example, so we just set all of these values to 1. So this is our finished UCF file. So as you can see here, we've got the same as before, we've got all of our atoms, and then we've got all of our interactions. So we've got 144 interactions, all with an interaction strength of 1. So 144 is 8 times 18, as we expect. So the first column, interaction number, goes from 0 to 143, as expected. And then this second column here is every interaction that occurs between every atom. So these are our nearest neighbour interactions. Most of these occur, as you can see, between atoms in the initial unit cell. So all of these are 0, 0, 0. So atom 0 interacts with atom 1, atom 0 interacts with atom 2, and atom 0 interacts with atom 4. And for all of these are in the same unit cell, and then we move on to other interactions which are not in the same unit cell. So this is in the unit cell above the initial unit cell. This is sideways in Y, and this is sideways in X. And this is the same for all of the interactions in this list. So now we have created our unit cell file. What we need to do is we need to look at our material file. So this is our material file. Our number of materials is 2, 1 for each sublattice. So both of these materials are basically going to have very similar properties, apart because they're both just simple antiferromagnetic materials. So I've just set the damping constant to 1, spin moment 2.6, the initial spin direction to random, and then I've set a ferromagnetic exchange between atoms in the same sublattice and an antiferromagnetic exchange between atoms in different sublattices. So this can be seen from the negative exchange between material 1 and material 2, material 2 to material 1. So now what we want to do is we want to run a really simple field cool simulation. So from this, we're going to calculate the Néel temperature of our antiferromagnet. I'm not sure you've done a field cool simulation before, but it's very similar to a magnetization versus temperature simulation. But instead of increasing the field, instead of starting at 0 Kelvin and then slowly increasing the temperature, what it does is it starts at a high temperature and then slowly decreases it. You can also set a cooling function and a cooling time. So it has slightly different parameters to the M versus T simulations that you've run before. But apart from that, everything is pretty much the same. So here what we've output is time, temperature, magnetization, and then we've printed to screen the temperature and the material magnetization. This is just so that we can see how the simulation is getting along as we run it. Now, so we're going to run the simulation using the terminal. So I've got this folder called Anti-Ferromagnets, and in it I've got my .mat file, my UCF file, and my input file. So all of these are exactly the same as the ones you've just seen on the slides. 2 by 2 by 3 nanometers, periodic boundary conditions, and then I'm running a field cool simulation. So I've got my afm.mat file, exactly the same as the one that was just on the slide, and then my unit cell file that we've just created. Okay, so what I want to do is I want to run Vampire. So my Vampire folder, so I'm just going to run it in serial, and there we go. It's running, it's slowly cooling, as you can see. So that is our simulation completed. As you can see here, I've created lots of spin configuration files, but we've also got an output file. So if we have a look at our output file, as you can see, it has time, temperature, and then magnetization. So mx, my, mz, and ml of magnetization length of the first material, and then mx, my, mz, and m length of the second material. So as you can see, at the moment we're at 800 Kelvin, which is quite high, so the magnetization length is very, very small. But if we go down to the bottom of the file, at almost 0 Kelvin, the magnetization length has increased to almost 1. So what we want to do is we want to plot this. So if we look at our output file, and we want to see what columns we want to plot, so we want to make a magnetization versus temperature curve. So temperature, column 2, and then magnetization length is columns 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we want to plot this in GNU plot. So we want to do plot output using column 2 and column 6. So here is the graph that we've created. Change that to a point. But if you remember, we had 2 sublattices. So we were only looking at sublattice 1. So what we can do is we can then do exactly the same again, and we can look at sublattice 2 as well. So as you can see, they both have very, very similar magnetization versus temperature patterns. So the Néel temperature of both of these materials looks very, very similar. So what we normally do for an antiferromagnet is we actually take the average of the 2 sublattices. So if instead of plotting them separately, we take an average, so column 6 plus column 10 divided by 2. So as we know, antiferromagnets are magnetically neutral, so if we just added the magnetization of the 2 sublattices, it would go to 0. However, if we look at the magnetization length of either of the sublattices, as we've just plotted in GNU plot, you can see that at low temperatures, each sublattice has a very strong magnetization. So we take the magnetization of the antiferromagnet to be the average magnetization of the two sublattices. So we've done M equals M1 plus M2 divided by 2. And then from this, we can fit as you would for a normal ferromagnet. You can then, if you want, use the visualization tools which are inbuilt into Vampire to visualize the structure. So here I've visualized the magnetic configuration using Rasmol or Vesta. So this is just the crystal structure. So as you can see, it has the predicted crystal structure that you would get if you copied our unit cell in X and Y. So the yellow and the white atoms represent different materials. And then what I've done is I've used Povray to create a picture of what the spin configuration looks like. So here you can see that the magnetization of the red atoms is pointing away from us and the magnetization of the blue atoms is pointing towards us, giving us the predicted antiferromagnetic structure. And as you can see, we've got planes of blue, red, blue, red, blue, red. So this has been an introduction into how to create antiferromagnetic structures in Vampire. So this is just a tutorial for a simple uniaxial antiferromagnet. In another video, I'm going to go through how to create more complicated antiferromagnets, such as manganese to gold.